All right, let's take a look at example 6, the falling ladder problem. A 13-foot ladder leans against a vertical wall. So we have our vertical wall over here on the left. All right, it makes a right angle with the ground. The lower end of the ladder is pulled away from the wall at a rate of 2 feet per second. So the ladder is going to slide to the right, which of course is going to bring the top of the ladder down. And that's what we're going to try to find. How fast is the top of the ladder coming down the wall? Now we have a specific time that we want to look at, the moment that the top of the ladder is 12 feet above the ground. So in a second we'll go off to the side and draw a little snapshot of what's exactly happening at that moment. All right, but first we need to set up our drawing over here by labeling all the parts. All right, so since the ground is horizontal, we're going to label it X, and the wall is vertical. Let's label it Y. The slanted ladder here, let's label it Z. Right, so we need to find something that relates, an equation that relates X, Y, and Z together, and that's going to be the Pythagorean theorem. So x squared plus y squared equals z squared. And we're going to differentiate this with respect to time. Right, so the derivative of x squared with respect to t is going to be 2x dx dt. The derivative of y squared with respect to t is 2y dy dt. And the derivative of z squared with respect to t is 2z dz dt. All right, now let's talk about what all of our unknowns are. All right, we have x, we have y, we have z, dx dt, the rate of change horizontally, dy dt, the rate of change vertically, and dz dt, the rate of change of the ladder. All right, so we're told that the ladder is being pulled away from the bottom of the building at a rate of 2 feet per second. So since x describes the horizontal movement, dx dt must equal positive 2 since it is increasing its distance from the bottom of the building. Right? So that's getting plugged in there for the dx dt. All right, now let's take a look at what the values of x, y, and z are going to be at exactly the moment the ladder, the top of the ladder is 12 feet above the ground. All right, so I'm going to go out here to the side and draw my little snapshot. Okay, the picture of what's happening exactly when the ladder is 12 feet above the ground. Well, it's a 13-foot ladder, right? And this is a Pythagorean triple, so this side has to be 5. Right, so x is going to equal 5 at this moment, y is going to equal 12 at this moment, and z is going to equal 13 at this moment. So we're going to dump all those values into our related rate equation here. Right, so let's go ahead and plug everything in and see what we're left with. We have 2 times x times the rate of change of x, which is 2, plus 2 times y times the rate of change of y is what I'm trying to find up here. I'm sorry, right here. How fast is the top of the ladder coming down the wall? So dy dt equals 2 times 13 times dz dt. Well, if I take a look at our related rate equation, we still have 2 unknowns, and we can't solve a single equation with 2 unknowns. So let's think about this part here, dz dt, and what does that actually mean? dz dt is the rate of change in the length of the ladder. The length of the ladder is 13, so it never changes. this has to be equal to 0. All right, let's bring everything else straight down. Let's actually go ahead and combine some of this. 2 times 5 is 10, times 2 is 20, plus 2 times 12 is 24, dy dt. It's going to equal 0 on this right side. If we solve for dy dt, we're going to have negative 20 over 24, which is going to reduce to negative 10 over 12, or negative 5 over 6 feet per second. All right, now I want to go back and I want to point something out that I could have started with that might have simplified our work slightly. All right, our original equation, x squared plus y squared equals z squared. All right, we were told originally that the ladder is 13 feet long and leans against a vertical wall. Since this 13-foot ladder never changes its length, we're allowed to put that constant into the original equation that relates the vertical distance and the horizontal distance. So we could have had x squared plus y squared equals to 13 squared, right? And then take the derivative with respect to time. Now I'm only allowed to put this number in, this 13 in, since it stays constant throughout the problem. Any lengths or angles or volumes or areas that are changing must be put into the original related rates equation as a variable. All right, but this gives us 2x dx dt plus 2y dy dt equals to the derivative of 13 squared. The derivative of any constant is going to be 0. And then we can finish the problem up just as we did before. And you'll still get dy over dt equals to negative 5 over 6 feet per second.